This presentation is about inertial navigation history. Why do we study history? Consider the statement by the famous British philosopher George Santayana. If we don't study history, then we are doomed to repeat the mistakes of the past. Inertial navigation is a science that began principally in the late 20th century, and we will discuss some of the remarkable achievements that have been made in the following 75 years. Our methodology will be mostly to discuss the people who made major contributions to inertial navigation. Many of inertial navigation's concepts can be understood quite completely from Isaac Newton's third law. Newton was one of the greatest physicists, along with Albert Einstein, of all time. Newton's third law, particularly F equals ma, can be used to explain and derive most aspects of inertial navigation. Einsteinian physics, although relevant, is not really necessary to develop the mechanization of inertial navigation. The gyroscope is the key sensor for inertial navigation. The gyroscope accuracy is most important for an accurate inertial navigator. The first gyroscope was attributed to Leon Foucault, the Frenchman, in 1851. Of course, there were spinning tops before that. However, Foucault was the first one to make a gyroscope that could stay aloft for about 10 minutes. There were no electric motors then, so it was string powered. And along with his Foucault pendulum, helped to demonstrate the fact that the Earth rotated. In 2001, the Institute of Navigation celebrated 150 years of the invention of Foucault's pendulum. This is a picture of an original Foucault gyroscope, of which there are a few original ones still in existence. The inner gimbal of the Foucault gyroscope was balanced on a knife-edge bearing, and the outer gimbal was suspended by a fine torsion-free thread in such a manner that the lower pivot point carried almost no weight. The gyro was spun externally with a gearing mechanism. It was spun to 9,000 to 12,000 revolutions per minute before being placed into position, which was sufficient time to balance the gyroscope and carry out about 10 minutes of experimentation before the inevitable frictional forces caused angular momentum changes. The Foucault gyroscope was also used to demonstrate the Earth rotation, although the Foucault pendulum, which is in many cities in the world, including wonderful exhibits in Philadelphia and Washington, D.C., the Foucault pendulum was more prevalent in exhibiting the rotation of the Earth. England, France, and Germany were the great technological centers of the 19th century. Amongst the controversies associated with navigation was whether the German Johann Bonenberger demonstrated the gyroscope before Foucault. Also, the Englishman Sir Isaac Newton was thought to have experimented with a primitive version. There are some references that do appear to corroborate that the German Bonenberger did indeed have a working prototype in 1831, which is 20 years prior to Foucault. See, for example, the Institute of Navigation Historian newsletter article of summer 2008 for examples of controversies in attributing accomplishments in navigation. These slide presentations will not attempt to resolve the controversies, and the viewer is encouraged to do their own research. Other than for research and the aforementioned demonstrations of Earth rotation, gyroscopes did not have much particular applications prior to the early 20th century. By then, a major stimulus was the fact that virtually all warships were now made of iron. Magnetic compasses, which had served as the primary directional instrument on ships since the 15th century, was subject to the disturbances of the ferrous materials. And although hard and soft iron compensation methods were possible, gyro compasses using mechanical gyroscopes were being developed by Anschutz Kampf in Germany and Sperry in the United States by the second decade of the 20th century. Gyro compasses are the predecessors of inertial navigators and share much of their componentry. They require precision instrumentation that first became available after the industrial revolutions in Western Europe and America. Precision mechanical gyroscopes with drift rates less than a degree per hour were key to the advancements made by the German Anschutz and the American Sperry gyroscope companies. These gyro compasses were not subject to the magnetic fields of the ship. Another major navigation controversy arose as far as the patent rights for the gyro compass. During World War I, with the large buildup of warships, both companies garnered major profits from their gyro compass sales and were anxious to establish their patent rights. In the last slide, we refer to the patent process between Anschutz and Sperry. Well, it turned out that Albert Einstein, who was the world's most famous patent officer from about 1902 to 1909 in Switzerland, was also an avid sailor and a friend of Anschutz. To my knowledge, Einstein did not help Anschutz on their gyro compass efforts with any of his own scientific expertise, although it would be an understatement to say that he could well understand all the technology associated with gyro compasing. Einstein, in 1915, served as a patent consultant for the court during the patent litigation between Anschutz and Sperry. During that year, Einstein was completing his monumental general relativity work, often referred to as mankind's greatest singular intellectual achievement. Einstein perhaps should have recused himself from the task as a patent consultant, but in any case is not reported to have distinguished himself in that capacity. Anschutz went on to win the decision of the court. Both companies continued to flourish for several more decades as gyrocompass manufacturing and other inertial instruments became important for naval ships. Although Einstein's contributions to gyrocompassing may have been minimal, his imprint on navigation in the form of special and general relativistic clock corrections for GPS, the equivalence principle for accelerometers, and the laser gyroscope, and potentially for the atomic interferometric senses, has been tremendous. Elmer Sperry was the American inventor responsible for many advances in the utilization of inertial sensors. These applications included the aforementioned gyrocompass, and also included bomb sights and ship attitude stabilizers. The Sperry Corporation, founded in Brooklyn, New York by Elmer Sperry in 1909, later expanded to be an international purveyor of navigation and aviation instrumentation. In its various merger and acquisitions instantiations as Sperry Gyroscope, Sperry Systems Management, Paramax, Unisys, Litton, and Northrop Grumman, the Sperry name remains as a formidable inertial navigation cachet. This is a picture of a dual gyrocompass system aboard a German vessel in 1938. Prior to the development of miniaturized electronics and computers, the size, weight, and power constraints of this type of instrumentation was formidable. Today, an equivalent performing gyrocompass might occupy a couple cubic feet. Robert H. Goddard was an American scientist. He is most famous for developing rocketry in the first 2 decades of the 20th century. His rockets flew close to the edge of space. In terms of inertial navigation, Goddard was probably the first person to utilize gyroscopes to maintain attitude stability for the rockets. His work and publications were known to be read by the Germans, who subsequently took his work and advanced it for more sophisticated rockets. Inertial navigation evolved in much the same manner as many of our technologies. They are technologically Darwinian. Schuller's cousin, Hermann Anschutz Kampf, founded a firm near Kiel, Germany, to manufacture navigational devices using gyroscopes. In 1906, Schuller joined this firm. For many years, they struggled with the problem of maintaining a vertical reference as a craft, whether it be a ship or an early version of an airplane, moved around on the surface of the Earth. In 1923, Maximilian Schüler published his discovery that if the gyrocompass was tuned to have an 84.4-minute period of oscillation, this is known as the Schüler period, it would resist errors due to sideways acceleration of the ship or aircraft in which it was installed. In 1938, Dr. Walter Wrigley, a student of Draper, wrote his doctoral dissertation at MIT on the vertical integration from a moving base. The technology had evolved so that the servo loop closed around the gyrostabilized pendulum instrument of physical dimensions that could be electronically tuned to the required periodicity. Schüler, as is often the case, was before his time. He had most of the ideas correct, but not the technology to implement it. The Russians also apparently understood the principles of inertial navigation, but like the Germans, did not have the technology to create practical systems. People such as Walter Hussermann, J.M. Coy, and Reich appear to have been the systems thinkers in the field of Germany. Schüler and Boykow, though earlier in the field, were instrument-oriented rather than system designers. In the context of modern inertial navigation systems, the Schüler loop represents an error modality due to the inability to track the gravity vector, resulting in leveling errors referred today as tilts. Navigation and computers, especially inertial navigation, share a special symbiosis from a historical and functional perspective. As a dead reckoning device, an inertial navigator must at least perform the computations of integration from acceleration to velocity and then from velocity to position. Shown is a mechanical contraption made of a combination of gears and cams that took inputs from a gyrocompass and speed log and provided distance traveled computations. This is a picture of another mechanical contraption that was aboard a ship circa 1930 that did dead reckoning plotting with inputs from a gyrocompass and speed log. This is a predecessor to inertial navigation, as inertial navigation is also a dead reckoning device. The first modern digital computer is often attributed to this one shown at the University of Pennsylvania in 1946. It consisted of a large room filled mostly with electronic vacuum tubes, as semiconductor electronics had not yet been utilized for at least another 15 years. Advancements in computers and related electronics are closely linked, chronologically and technologically, to advancements in inertial navigation. The most advanced usage of inertial sensors for guidance and navigation is most often attributed to the Peenemünde Army Research Center group working for the German military during World War II. Werner von Braun was a principal scientist at Peenemünde. After World War II, German rocket scientists were coveted by the United States and the Soviet Union and gave these Cold War antagonists considerable expertise in inertial navigation and rocketry. Von Braun joined the Redstone Arsenal in Alabama after World War II, where he contributed to several American initiatives in guidance and propulsion technology. This picture, courtesy of Neil Barber of Draper Labs, shows the German V-2 rocket, which was utilized against major Allied cities, especially London, in the latter parts of World War II. Although its ballistic capabilities rendered havoc on the London population, fortunately, the V-2 attacks came too late in the war to have an appreciable impact on the war's conclusion. As Germany collapsed, teams from the Allied forces, the United States, the United Kingdom, and the Soviet Union raced to capture key German manufacturing sites and technology. Werner von Braun and over 100 key V-2 personnel surrendered to the Americans. Eventually, many of the original V-2 team ended up working at the Redstone Arsenal. The U.S. also captured enough V-2 hardware to build approximately 80 of the missiles. The Soviets also gained possession of the V-2 manufacturing facilities after the war, re-established V-2 production, and moved it to the Soviet Union. This is a picture of the guidance system for the German V-2 rocket. The V-2 was guided by 4 external rudders on the tail fins and 4 internal graphite vanes in the jet stream at the exhaust exit of the motor. One can see the gimbals and the gyroscopes in this picture. The guidance system consisted of 2 free gyroscopes, a horizontal and a vertical, for lateral stabilization, and Pigger accelerometers. Pigger stands for Pendulous Integrating Gyro Accelerometers, to control engine cutoff at a specified velocity. The V-2 was launched from a pre-surveyed location, so the distance and azimuth to the target were known. Fin 1 of the missile was aligned to the target azimuth. Some later V-2s used guide beams, that is, radio signals transmitted from the ground to keep the missile on course. But the first models used a simple analog computer that adjusted the azimuth of the rocket, and the flying distance was controlled by the accelerometers. The accelerometers controlled the flying distance such that the rocket stopped accelerating as soon as it reached the top of its approximately parabolic flight curve. The V-2 guidance system is generally not considered the first inertial navigation system because it did not perform integrations of velocity to the position level. The V-2 was considered the world's first long-range guided ballistic missile. The missile had a liquid propellant rocket engine and was developed as a vengeance weapon assigned to attack Allied cities as retaliation for the Allied bombings against German cities such as Dresden. The V-2 rocket also became the first artificial object to cross the boundary of space, with the vertical launch on 20 June 1944. As Donald Mackenzie in his book Inventing Accuracy said, it is a cogent reminder how technological excellence can be harnessed for evil motives. Charles Stark Draper is often recognized as the leader of American efforts in inertial navigation. During World War II, he developed bomber sights utilizing gyroscopes from his MIT work, and those bomber sightings were used to shoot down successfully Japanese kamikaze airplanes. After World War II, Draper's interest shifted from fire control, and he began the all-consuming task of developing inertial navigation equipments. One of Draper's first challenges was to convince the powers that controlled the purse strings that inertial navigation was indeed feasible. The equivalence principle, a consequence of Einstein's general relativity, states that it is impossible to distinguish between the force due to kinematic accelerations and gravitational force. Since it is the kinematic accelerations that an inertial navigation computer needs to integrate into velocities and then velocities into position, it was reasoned that a precise knowledge of the magnitude and direction of the gravitational force was a prerequisite for inertial navigation to be feasible. George Gamow, a renowned Ukrainian scientist who emigrated to the United States in 1934 and was a friend of Albert Einstein and a contributor to the Big Bang Theory, declared that inertial navigation is not feasible because of the equivalence principle. It was the pugnacious Charles Stark Draper, also a member of the Science Advisory Board, who challenged Gamow and won over the influential Science Advisory Board. In the midst of the Cold War, this enabled an influx of funding for inertial navigation. These MIT Instrumentation Laboratory gun sights utilize servo mechanisms that incorporated gas-bearing single degree of freedom gyroscopes developed by the MIT Instrumentation Laboratory. These gyroscopes also applied to future spacecraft and spacecraft boosters, and also became implemented in ships' navigation systems. His systems were the prototype for many commercial transport automatic navigation systems, as well as those applied to military aircraft. In August of 1945, Draper had proposed to the Armament Laboratory of the Air Force's engineering activity at Wright-Patterson Air Force Base that he build a stellar bombing system. The report included a statement to the effect that robotizing the system for use with guided missiles was feasible. During the Cold War, roughly from 1948 to 1980, the United States, the world's richest nation, had virtually an unlimited budget for advanced defense products. Two of those products were the Snark and the Phoebe. These were drone, unmanned bombers, which both had stellar inertial systems. The Snark was built by Northrop Corporation, and the Phoebe was a MIT AC spark plug collaboration. Shown here is a picture of a descendant of the Phoebe in 1954. The Stellar systems were necessary to aid the inertial systems. By the end of World War II and the onset of the Cold War with the Soviet Union, the defense budget was large enough to incentivize many of the United States major companies such as Armour, Bendix, Corvair, General Electric, MIT, North American Aviation, Sperry, and others to develop navigation systems that were based on inertial sensors. In particular, inertial sensor navigation, which did not have a dependence on radio navigation or other sighted systems, were in particular demand for long-range bombers. By around 1950, the black box navigation work at Aeronautics, a division of North American Aviation, and at the MIT Instrumentation Laboratory resulted respectively in the XN series of inertial navigators for the Navajo missile and the Phoebe, named after the sun god Phoebus, stellar inertial bomber navigation system. In his book, Inventing Accuracy, Donald Mackenzie emphasizes that the creation of the new technology of inertial navigation cannot be captured by the traditional notion of invention with its singular, crucial eureka moment. Rather, it is described as a triumph of heterogeneous engineering encompassing the accomplishment of a vast number of individuals and organizations. The XN-1 was one of the first all-inertial systems that successfully assisted in navigating an aircraft. That is, it used techniques that relied entirely on self-contained devices, including accelerometers, gyroscopes, and computers, with no reference to outside information such as radio signals or visual sightings of the ground or stars. However, very little information on its actual performance or accuracies could be found, and the North American aircraft established as the Aeronautics Division in 1955 soon started the XN2 program, which did involve celestial navigation. In any case, several people indicate that the XN1 in May of 1950 demonstrated the capability of pure inertial navigation. Aeronautics originated in North Aviation's Technical Research Laboratory, a small unit in the Los Angeles Division's Engineering Department in 1945. In 1946, the laboratory won an Army Air Force contract to develop a 175 to 500 mile range glide missile. The work and the lab expanded so that by June 1948, all of this laboratory was consolidated at Downey, California. The evolution of the Navajo missile then resulted in the establishment of Aeronautics as a separate division of the North American Aviation in 1955, first located in Anaheim, California. Aeronautics included the Navigation Systems Division, designing and producing inertial and stellar inertial navigation systems for ships, submarines, missiles, aircraft, and space vehicles. MIT Instrumentation Laboratory and Aeronautics for several years were the premier, although not the only, producers of inertial navigation systems. During the early 1950s, Charles Stark Draper's team at MIT developed a prototype pure inertial reference system to guide submarines, missiles, and aircraft, known as the Space Inertial Reference Earth, SPIRE. It used gyroscopes and accelerometers connected to a computer to determine position without emitting signals that could reveal position or relying on external signals that might be vulnerable to enemy interference. On February 8, 1953, SPIRE guided a B-29 from New Bedford, Massachusetts to Los Angeles entirely under automatic control. Many regard this as the first truly successful demonstration of inertial navigation. It ushered in the rapid adoption of inertial navigation systems by the U.S. Navy and Air Force. In 1953, digital computers and displays were not widely available. This is a picture of the controls used for the aforementioned SPIRE. Although the Navajo missile program was canceled, the XN series of inertial navigators that first flew in 1950 became the basis for the N6A inertial navigator, mostly developed by Audinetics, and went on to fame in 1958 by navigating the USS Nautilus and the USS Skate on historic transpolar missions to and under the North Pole. It also became the basis for the N7, which bore the designation SINS, or Ship's Inertial Navigation System. In 1958, the Nautilus went under the North Pole, 90 degrees latitude and an indefinite longitude. Interestingly, from this log, it shows the Mark 19 as being the reference for navigation, but it also points to the N6A data. The Navy's Polaris program, designed to launch from submerged submarines intercontinental ballistic missiles, had a clear need for covert navigation. That meant that inertial navigators were particularly applicable to Polaris submarines. The masked series of inertial navigators developed by the Instrumentation Laboratory of MIT and the N6 series of inertial navigators developed by Audinetics both contributed to the development of the ship's inertial navigation system that went on Polaris submarines in 1960. Submarines, because of their inherent covert missions of long duration, require the highest quality inertial navigators. Historically, the Strategic Systems Project Office, administering the Polaris, Poseidon, and Trident projects, has made major contributions to high-accuracy inertial navigation. The major American defense industry giants of the time, North American Aviation Audinetics Division, now part of Boeing Corporation, Sperry gyroscope, now associated with the Northrop Grumman, and Lockheed Martin, as well as the MIT Instrumentation Laboratory, now known as Charles Stark Draper Laboratories, collaborated in developing the marvels of precision that were the inertial navigators on submarines. Shown here is a Mark II SINS, which with its various mods has been on strategic submarines from approximately 1960 to 2005. The gyroscopes are of the mechanical gas-bearing type, and the gimbals maintain orientation of the inertial sensors to the northeast down coordinate frame. Random drift of the SINS gas-bearing gyroscopes was the principal error source for long-term positioning accuracy, stemming from research performed in the early 1950s by Professor Arnold Nordisek of the University of Illinois. An electrostatically suspended gyroscope offered the ultimate potential for reducing random drift by maintaining a spinning beryllium ball suspended in a vacuum and levitated by an electrostatic field. Honeywell Corporation was the first company to capitalize on Professor Nordisek's electrostatically suspended gyroscope. They produced some of the most accurate ESGs. The ESGs eventually went on submarines, both attack submarines and boomers for both the United States and the Soviet Union. The ESG also went on several other platforms, such as the B-52 bomber, and was in Trident submarines up to at least 2022. Gyroscopes are the key element for inertial navigation, and their performance has improved by about 5 orders of magnitude over the decades from 1950 to 1990. The ESG remains as the gyroscope with the smallest random drift on the order of microdegrees per hour, but over the years there have been many different types of gyroscopes produced by many different companies and countries. Pictured here is a single degree of freedom floated mechanical gyroscope utilized by the French company Sagem and in some Singer Carefat systems. The brief history presented in this presentation pays insufficient due to European and Soviet Union efforts in the development of inertial navigation. Companies such as Sagem in France, Thales in United Kingdom, Anschutz and Litef in Germany, Ixier and Xblue in France also produced high-quality inertial navigation systems. Also, the Electro-Pribor Institute in St. Petersburg, Russia, was a leader in high-accuracy systems for many years. The Soviet Union's nuclear submarines employed an inertial navigator with electrically suspended gyroscopes similar to those employed by the U.S. submarines. 1. The U.S. Navy recognized that inertial navigation had critical importance for aircraft navigation. They built a special purpose facility in Warminster, Pennsylvania, for testing inertial sensors and inertial systems. The site was chosen within the property of the Naval Air Development Center based on its proximity to stable bedrock. The Inertial Sensors Laboratory within the larger circular structure shown above, included 12 granite test piers, which are bonded to the bedrock. Amongst the unique characteristics of the building are an outer wall and center hub with vibration isolation material between the upper and lower footings to attenuate building-generated vibrational disturbances, a concrete floor constructed of individual slabs of concrete with 3/4-inch expansion joints between slabs to reduce the vibration transmitted from one part of the facility to another, and a housing of all basic utilities within a separate, isolated mechanical building shown in the above picture as the smaller circular construction site. From 1964 to 1996, this inertial facility was used to test many of the Navy's inertial sensors as well as aircraft and ship inertial navigation systems. Amongst the gyroscopes tested were early ring laser and electrostatically suspended gyroscopes, which were being developed to replace the existing generation of mechanical gas-bearing gyroscopes. After a series of reorganizations transferring control of the inertial facility from the Aircraft Instrumentations Laboratory to the Naval Air Development Center and then to the Naval Command and Control Ocean Surveillance Center, the latter was closed in November 1996 as a result of a base realignment and closure action, BRAC. However, no government reorganization or realignment could affect the stability of the building. The facility was transferred to the Applied Research Laboratory of Pennsylvania State University via a federal land reuse authority from the Department of Education through a public benefit education conveyance on November 10, 1999. From 1996 to the present, 2024, the facility is being operated by the Penn State Applied Research Laboratory and continues to test advanced gyroscopes, accelerometers, and navigation systems. It specializes in the most accurate inertial navigation systems being developed for attack and boomer-class submarines. Illustrated in the above slide are some sensors and systems that have gone through research, development and test, and have transitioned to the fleet where applicable. They include systems for virtually all naval aircraft and submarines. Optical gyros, here shown as a ring laser gyro, had the attributes of theoretically having no moving parts, although most laser gyros as manufactured did have moving dithering mirrors. In any case, Warren Masick of Sperry Corporation in 1963 is attributed to demonstrate the first laser gyro. Sperry, as you remember, also made major contributions to MIT Instrument Lab's development in the early 1950s. Sperry also later on did manufacture their own laser gyros, not for inertial navigation systems, principally for stabilization systems for ships. In this sense, Sperry was very generous in divesting of their knowledge on gyroscopes to the rest of the community. Over the next 15 years after 1963, the ring laser gyroscope emerged as the preferred gyroscope for aircraft inertial navigation systems. Its attributes of ruggedness, minimal moving parts, and direct digital output complemented other ongoing trends in aircraft inertial navigation. That is, gimbal-less strap-down systems and high-speed digital computations. Although the Sperry Corporation was the first to demonstrate a laser gyroscope, it was the Honeywell Corporation during the decade from 1965 to 1975 that innovated refinements to the laser gyroscope, leading it to become the dominant avionics gyroscope technology for the next 25 years. Honeywell Corporation, principally out of their Minneapolis office, was the major purveyor of ring laser gyros, at least in the United States. Its 1308 series was used in smaller UUVs and smaller tactical missiles. In general, the circumference of a laser gyro is inversely proportional to its accuracy. That is, its accuracy improves the larger the size of the laser gyro. The 1342, the dimension 42 refers to 4.2 inches on a side of the triangle of the laser gyro, was used in its high accuracy ship navigators. The 1389, or 8.9 inches on a side, to my knowledge was never used because it was too large to fit in a submarine hatch. So the principal RLGs were the 1308, the 1320, which was its most prolific laser gyro, used in embedded GPS inertials and aircraft avionics, such as the Honeywell 764 and that class of EGIs. The 1342 was used in the WISN 7, which is a shipboard inertial navigator. Richard Shorthill is generally given credit for demonstrating the first fiber optic gyro. He was a University of Utah professor and a Boeing senior scientist. The fiber optic gyro has certain advantages over the laser optical gyro in that its signal-to-noise ratio can be increased more effectively without increasing the volume of the device, and its manufacturability is considered better than the ring laser gyro. For that reason, starting in about 1998, the ring laser gyro felt inferior to the fiber optic gyro, and many avionics systems began transitioning to the fiber optic gyro. Even the high accuracy strategic systems program started to develop a fiber optic gyro beginning in the late 90s and transitioned in the early 2020s. This is a picture of a vintage 1980s laser gyroscope on the left and a fiber optic gyroscope on the right. The optical gyroscopes have dominated the avionics market since the late 1970s. The Sagnac effect, also called Sagnac interference, named after the French physicist Georges Sagnac, is a phenomenon accounted in interferometry that is elicited by rotation. The previous gimbal-mounted mechanical gyroscopes used the principle of conservation of angular momentum as a rotational reference for an inertial navigation system. With the development of so-called laser gyroscopes and fiber optic gyroscopes based on the Sagnac effect, the bulky mechanical gyroscope is replaced by one having no moving parts, or few moving parts in the case of a dithed motor ring laser gyro. The principles behind the two devices are different, however. A conventional gyroscope relies on the principle of conservation of angular momentum, whereas the sensitivity of the ring interferometer to rotation arises from the invariance of the speed of light for all inertial reference frames. The basis of the Sagnac effect on the Einsteinian relativistic principles was ironically rejected by Sagnac, possibly for anti-Semitic reasons. The fiber optic gyro made major inroads into the dominance of the ring laser gyro by the early 1990s, and high accuracy versions of the fogs have been developed for long duration ship and submarine markets. These high accuracy fog gyros have fiber lengths of between 3 and 10 kilometers. This lecture is about inertial navigation history, but the impact of GPS should also be noted. When the first GPS satellites were launched in 1976, and then the entire system became fully operational in 1995, there were those who thought that GPS might not only replace all other radio navigation aids, but would also lessen the importance of inertial navigation. This was definitely not true, but the combination of GPS plus inertial navigation yields a system that has been called a marriage made in navigation heaven. Their complementary attributes are shown in this slide. As a radio navigation system, GPS will always have vulnerabilities to jamming, obscuration, and under certain circumstances, spoofing. Inertial navigation is inherently autonomous and invulnerable. However, its errors can grow unbounded in time. Notably, for many weapon systems, inertial navigation's provision for attitude and velocity at high data rates are critical, which GPS does not enable. On the other hand, GPS provides bounded position and also provides highly accurate time. That marriage made in navigation heaven can be further illustrated by the above flow diagram. Starting at the bottom circle, if the ins is provided good accuracy, position, and velocity from GPS, then it improves the accuracy of INS error estimates. This in turn, moving up towards the left, this in turn provides higher quality INS velocity, aiding to the GPS, which in turn allows the GPS receiver to narrow its GPS tracking loops. By narrowing its GPS tracking loops, it lets in less noise, thereby improving the system anti-jam performance. This in turn increases GPS availability in high jamming tactical missions. Completing the circle, getting improved GPS accuracy for INS error estimates. The GINA, the GPS Inertial Navigation Assembly, was probably the first embedded GPS INS built for the Navy for the T-39 trainer. This is an example of a similar system built somewhat later by Honeywell, the H764 GPS, which also featured an embedded INS by Honeywell, and associated with it was a Rockwell Collins embedded card. The typical GPS INS had the capability, theoretically, of providing 3 different navigation outputs: a GPS alone solution, an inertial navigation alone solution, and a hybrid solution, which provided an optimal combination of GPS and INS. This program evolved into what was known as the EGI program, administered by Wright-Patterson, which supplied most of the embedded GPS inertials for many of the Navy aircraft and many of the Air Force aircraft. This slide goes through the history of gyro development as prepared by Honeywell Corporation. The first gyro applications for navigation were in gyro compasses, and they were mechanical gyros, spinning moment of inertia gyros. In the late 1950s and 60s, we began to have also mechanical gyros, tune rotor gyros, and other types of similar single axis mechanical gyros that are based on conservation of angular momentum. ESG was not a ion gyro, however, it was still based on the conservation of angular momentum, in that case a beryllium ball. Then in the 1980s, the optical gyros became dominant, beginning with the laser gyro, and then going to the fiber optic gyros. The optical gyros had lower cost, fewer mechanical parts, naturally digital outputs, and they were amenable, particularly for the strap-down gyros, or strap-down inertial systems, or gimbal-less inertial systems. Beginning in about 2000, the hope was that gyros could graduate to MEMS gyros for their producibility, lower cost. However, MEMS gyros have only began to take hold for the tactical type of inertial navigator, which means inertial navigators that have navigation performance on the order of 10 to 100 nautical miles per hour, growth of drift errors corresponding to gyro drift residual biases on the order of 1 degree per hour. So we hope going forward that smaller MEMS type gyros will come about. The quest for small, low-cost navigation gyroscopes is a quest that still remains. This is a slide from California Technical with a proposed MEMS Brillion optical gyro. It's optically based, similar to a Sagnac effect laser or fog gyro, but with, of course, different technology and miniaturized so that it would fit into an integrated circuit. I should emphasize that this is a proposed system that has not evolved into the production phase. The quest remains, and there remains many future research objectives available for the navigation systems engineer. We study history for its interest, as well as what lessons we may learn towards the future. With the megatrends towards autonomous vehicles and self-driving cars, emphasis on cybersecurity, artificial intelligence, and anti-jamming, clearly the future portends increased importance for the invulnerable, self-contained attributes of inertial navigation.